Welcome back, everyone. In this video we're going to start our discussion of magnetism. So we'll be looking at a number of topics, but what we should begin with is the source of magnetism. Where does magnetism come from? And then what kind of effects does magnetism have on point charges? So we're going to start this with a bit of an overview of magnetic fields, and then we'll talk a little bit about where magnetic fields come from. So magnetic fields, in essence, are formed by moving charges. Magnetic fields also affect charges that are moving through them. So this is sort of like an electric field in the sense that a charge can create a static electric field, and if you place another charge in an existing electric field, it will feel a force. So magnetic fields are the same. The unit is the Tesla, and that's going to be newtons per coulomb meter per second, which we can break down to newtons per amp times meters. But a common unit that you'll see for magnetic field is the Gauss, and 1 Tesla is 10 to the 4th Gauss. So let's consider what's going on at an atomic level. So here are some diagrams of 2 electrons, and these electrons have tiny little magnetic dipoles. So you can see the one on the left is pointing up and the one on the left is pointing down. In quantum mechanics, we talk about this as the spin. So you can see that this has a spin of +1/2 and a spin of -1/2. And so one way to think about an electron is that every single electron is like a tiny bar magnet. And this arrow right here sort of represents that bar magnet. Okay? And you can also see in green the magnetic field lines. So if we zoom out a little bit, then we're going to see some magnetic domains. And domains are just groups of lots of atoms that have similar magnetic field orientations. So you can see on the top here that this is what it looks like if a material is unmagnetized. You have many domains, but they are unaligned. But if it's magnetized, all the domains are lined up. And so if you think about a chunk of material as a bar magnet, the magnetic field lines actually pass through the magnet, which has many aligned magnetic domains. So the field lines come out of the North Pole and they wrap around and they go into the South Pole. And this is going to be important later because in a previous video, we saw that electric field lines spread out, they diverged, but that's not the case with magnetic field lines. Magnetic field lines form closed loops. That's very important. So then what's misleading about these pictures? Well, the most important thing about the first one is that there's no field being shown inside of the magnet, where all these bar magnets are pretty much aligned to have their north and south facing the same way. You get the idea. And then for the second one, not only do you have a field going across like this, but you have field that is forming all sorts of closed loops going outside of the bar magnet. So we have to be careful when we think about magnetic fields. You can also have, and we'll be talking about this a lot more in chapters 29 and 30, but you can have an electromagnet, and that's essentially a magnetic field which is caused by a current. So in this first picture here, we see a current or a wire, I, that has a magnetic field that's looping around it, and we'll talk more about this a bit later on. Here's another example. You can have a toroid that has current through it. It's basically a donut, and you can see the magnetic field in the green sort of wrapping around that. So the red represents the current flowing around like this. So that's that current. And the magnetic field lines are the green. And so here's another example of this. You can have two of those such rings, and that's called a Helmholtz coil if you arrange them in this fashion. And it has lots of applications. Okay, and here's one more example. How do we get a uniform magnetic field in which to run an experiment? Well, one easy way is to get some permanent magnets and to put a loop of wire in there and to run current through that wire. And that's going to give us a pretty uniform magnetic field. Another way that we can do this is if we take what's known as a solenoid and we apply an EMF or a voltage to a solenoid, we're going to get a magnetic field in that. Okay, so here's a picture of the Earth, and it's showing the magnetic field of the Earth, but something's very wrong here. So see if you can figure out what that is. So it turns out that the field lines are correct, but remember that magnetic field lines flow into the South Pole and come out of the North Pole. So a better picture would be this, that the Earth does have a bar magnet, but that bar magnet has a south magnetic pole at the north geographical pole of the Earth. And actually it's offset. There's a little bit of an angle of offset here. And if you've done some hiking in North America, you know that you have to account for the difference between magnetic north and geographical north. And I also want to go back to this because I want to show you that the magnetic field of the Earth is not always perpendicular to the surface. Here you see it coming in at an angle that's not very much. It's a very shallow angle to the surface. So really, the magnetic field depends on your location on Earth. So you have to be very careful about that. Okay, so let's recap what magnetic forces can and cannot do before we talk about how to calculate them. Magnetic forces can accelerate charged particles by changing their direction. They can also cause charged particles to move in circular or helical paths. Magnetic forces cannot change the speed or kinetic energy, and they also cannot do work. So these two things go together. So why is that? Well, we have to take a look at the magnetic force on a charged particle. And so here's our equation. The force on a charged particle is QV cross B. So it's a cross product, which means that if we have a magnetic field going one way and we have a velocity of a particle going another, those are at right angles, and the force will actually be at a right angle to those two. And because of this, since F is perpendicular to the velocity, that means that F is also perpendicular to dx, because velocity is dx dt. Because of this, work is going to be 0. So that means that the change in kinetic energy for a particle traveling in a magnetic field is going to be 0. Unless the magnetic field is changing, but we're not going to consider that now. So the magnitude of a cross product is QVB times the sine of the angle between the two vectors v and b. Okay, and in many of the cases it'll be 90 degrees, but not all. So Q is the charge in coulombs, V is the speed in meters per second, B is the magnetic field measured in Teslas, and theta is the angle between the velocity and magnetic field. Now one last thing, the direction of the magnetic force, because it's a vector. So this is the first of a couple of different right-hand rules. And if you were with us for the first semester and we studied torque together, remember that torque was basically R cross F. And so this is the same format. V, the velocity, is represented by, on your right hand, the direction of your pointer finger. B, the magnetic field, is the way that you point your other three fingers, so middle, ring, and pinky, or alternatively, it's the direction that you face your palm. And you should hopefully be thinking about this while watching this video. So look at your right hand, look at your pointer finger, and look at your palm. And then your thumb is going to be the direction of the magnetic force. So let's do a couple of examples. First of all, we're going to look at electric fields, and we'll contrast that with magnetic fields. And then later on, we're going to put them together. So we have P, we'll assume, is a proton, and we're going to sketch the path and calculate the acceleration. E is 2,000 newtons per coulomb, and V is 2,000 meters per second on the right. Okay, so on the left, well, we did this a couple units ago. F is equal to QE, and A is F over M, so A is just QE over M. You plug in all the numbers for this, and you get an acceleration of, about 1.92 times 10 to the 11th meters per second squared. And the direction, if it's a positive charge, it will have a force and therefore an acceleration in the direction of the field. Very simple. Okay, now on the right, where we have an electric field and we also have an initial velocity, we could say that x is basically Vx times t, but y is going to be Vy initial times t, which is 0, plus 1/2 a t squared. Now a is going to be the same thing, and in order to get t, we can rearrange that t is x over Vx, which is 2,000. So y is 1/2 times that extremely large value of a right there, and t is going to be x over 2,000 quantity squared. So that means that y is going to be equal to basically 24,000 x squared, which is a parabola that goes like this. Okay, now it's very important to note that this is a parabola. Okay, so that's the path. Now it should be a lot sharper than this. It probably is more like that. You probably won't, in real life, you won't even be able to tell it was a parabola because of this ridiculous acceleration value. Okay, now what if we replace the electric field with magnetic fields? So now we need to think about the magnitude and the direction. Okay, so first of all, we have that F is equal to QVB, the magnitude of F is QVB sine theta. Okay, so again, it's a proton, but on the left, what's our velocity? Well, our velocity is 0, and here's the kicker for magnetic fields. Nothing happens unless you're moving through it. So if the velocity is 0, the magnetic force is also 0. Nothing happens. So that's really boring. Okay, but on the right, we can calculate a magnitude of this force. And so the acceleration is going to be the magnitude of magnetic force divided by the mass. It's still a proton. So the mass of a proton, which I didn't mention in the previous slide, is 1.67 times 10 to the negative 27th kilograms. So the acceleration is going to be QVB sine theta over m. Now, if you look at this diagram, what is the angle between the magnetic field and the velocity? If you haven't seen these symbols before, an X means that something is going into the page. And again, this is something that we talked about when we studied torques, but if you didn't take mechanics, just know that an X is going into the page and a dot with a circle is something coming out of the page. So the X can be thought of as the tail of an actual arrow, right? The feathers of an arrow. And the dot would be the point of that arrow, the arrowhead. Okay, so the angle is actually 90 degrees if you look at this diagram, so we just have QVB over M, and I've calculated that out to be about 3.83 times 10 to the 11th meters per second squared. Okay, now, what's the direction of this force? Well, remember that V is represented by your pointer finger. So right now I want you to point your pointer finger on your right hand to the right. Okay? B is either the direction of your palm or the other 3 fingers. So I want you to point your right hand so that your palm is facing into the screen, whichever way that is for you, and your pointer finger is going to the right. So basically, you should have your hand on the screen and your thumb should be pointing up. And that's the direction of the force. Okay, so that's pointing up in this case. This is pointing into the page, and this is pointing to the right. So the magnetic force is going up. So what kind of path is that when the velocity is perpendicular to the force? We've seen that before, and that's actually circular motion. So this is going to carve out a circular path. Okay, and I don't have the space to draw all of it, but we'll actually look more at this later and analyze what kind of path we're going to get from a magnetic force. Okay, so next time we're going to be talking more about magnetic fields, and we'll be discussing the concept of magnetic flux.